Our proposal is a molten salt magnetohydrodynamic pump by Trevor Michelson
and Bradley Cart. We are two Alfred State College undergraduate students in the Mechanical Engineering Technology Bachelor Science program.
and our advisor is Dr. Joe Norwegian. This is for the senior seminar course, BSET 7001. So our motivation for this proposal was to create a realistic learning experience to prepare us for the engineering industry. We also wanted to further develop the underappreciated field of nuclear energy, which can lead to more sustainable sources of energy, particularly clean energy, since nuclear energy is very clean compared to other renewable sources with almost no carbon emissions whatsoever. And another reason we wanted to do this design was from a video from Tech Ingredients on YouTube, which first went through the theory of magnetohydrodynamic pumps, which talked about the basic applications of these in slightly mentioned nuclear energy. And that caused me to do some further research and ended up coming up with this proposal for a senior project.
What we will be covering in this proposal is our problem statement, our proposed solution to the problem, the contributions that our project will have to the field, a review of relevant literature that already exists in the field, our proposed design, the steps that we will take in our projects, the potential applications of our project, and our Gantt chart. One of the best mediums for thermal spectrum nuclear reactors is molten salt, due to its large liquid temperature range and its ability to dissolve nuclear fuel. Molten salt, however, is highly corrosive and requires high temperatures to melt. This works in our favor, actually, as the high temperature improves thermodynamic efficiency by giving a higher temperature range to work with. It does, however, create a environment which causes conventional pumps with moving parts to fail prematurely, which leads to frequent drop-offs in efficiency unless the parts are commonly replaced.
So this is a major problem, and we ended up wanting to come up with a solution that had no moving parts, as this would not experience the same wear due to caustic and high temperature environment. We did this through a magnetohydrodynamic pump, which is created using two electrodes and magnets to induce flow through the Lorentz force, which would feature no moving parts. This is very similar, or it's the exact same force actually, that electric motors use, except in electric motor applications, it's the wire that's moved rotationally through this force rather than a fluid directly that we're using. Now, the simplicity of a pump like this, due to the fact that it has no moving parts, reduces its overall cost to produce and maintain the pump, as well as reducing the chance of failure, which is imperative in nuclear reactors, as safety is extremely important, and this reliability helps increase and lower the chance of potential risk and failure.
The magnetohydrodynamic pump that we will be designing is specifically intended for use in a nuclear reactor. This differs from traditional uses of magnetohydrodynamic pumps, which were for propulsion in vehicles, theoretically in aerial vehicles, or more practically in marine vehicles, more specifically Soviet-era submarines. Also used in cold plasma torches and microelectrical mechanical systems with microchannels.
So for a literature review for this project, we did a variety of papers to see what has already been done in the field, and we found some studies on molten salts as well as magnetohydrodynamic pumps. So the first study we looked at was a study on molten salts and fusion technology by Moriyama, as well as 4 other engineers and scientists, found that molten fly salt to be one of the best mediums for nuclear reactors due to its high solubility of the uranium fuels, its chemical stability in these environments, its low vapor pressure, its stability under radiation, specifically in the reaction chambers. The molten salt doesn't really care how many neutrons and other radiation types it's bombarded with. It's stable. Its compatibility with other common materials such as steel, and its heat transfer conditions. Specifically, molten fly has a thermal conductivity of 1 watt per meter Kelvin, and it has a density of 1940 kilograms per meter cube. Specifically, FLIBE is a salt composed of two salts, which is lithium fluoride and beryllium fluoride. It's generally a 50-50 composition. And another study that we viewed did a performance analysis of magnetohydrodynamic pumps, but for sodium-cooled fast reactors. They're very similar to molten salt reactors, which is what our pump would generally be used in. However, sodium tends to be a little bit more dangerous due to, if it leaks, its contact with air can be catastrophic. However, they ended up finding that molten FLIBE in their study it flowed best at 650 degrees Celsius. So for our design concept for this, we essentially have a fluid flowing channel in the middle with two electrodes, one on each side, and a magnet either just on the bottom or magnet on each side to increase the efficiency of the Lorentz force. The reason for this is the Lorentz force is directly proportional to the magnetic field induced in the start. So if we start with magnets, the stronger the magnet, the better. It will increase the pumping capabilities of this pump. You can still pump that much, however, it will require much more current through the electrodes to produce the same amount. Now, the reason this works is because the fluid is electrically conductive and is full of negatively charged and positively charged ions, which can directly be influenced by that magnetic field and Lorentz force.
The system that we're going to be designing is going to operate at 650 degrees Celsius with a maximum temperature of 700 degrees Celsius. It will be pumping FLIBE salt between 5 to 10 kilograms per second through 6-inch Hastelloy end pipe, and it will be designed for a 10 megawatt nuclear reactor, which is small for most nuclear reactors, but is a size that is easily scalable. A second design will be properly scaled based on material properties relative to those of molten FLIBE. It will be made using Cerolo 136 alloy and acrylic piping for a much safer and less expensive demonstration.
So for the project steps overall, we're going to first gather materials for the demonstration model. This includes Cerolo 136 alloy, which is an alloy composed of lead, bismuth, tin, and indium. And the reason it's called Cerolo 136 is because it melts at 136 degrees Fahrenheit, which is a relatively low melting point for a metal, which makes it easy for us to use in a safe environment. We'll also need rare earth magnets to increase the Lorentz force for the pump itself, and as well as 1-inch acrylic pipes to transport the Cerolo 136, and finally copper plates as the electrodes in the pipe. Then we're going to design and simulate the fluid and heat flow in SolidWorks for both the theoretical for the 10 megawatt design as well as the demonstration design. Then we'll fabricate and assemble the demonstration model, and then using that model created, we'll test it and analyze the results to see if they compare to SolidWorks.
So as previously mentioned, the intent with this project is to create a pump that's scalable for various different size nuclear reactors, but it could also, the design could also be used for similar high temperature or caustic environments with pumping applications.
So this is our Gantt chart, and this is where we're currently at, which is in the middle of making the PowerPoint and video presentation. And this goes through step by step both processes and steps that we need to complete our project. Our first step was to gather and make the necessary materials, which we'll do over break, and then we'll create an initial design once we get back, followed by simulating the fluid flow in SolidWorks for both the demonstration and theoretical models, then followed by the heat, simulating the heat flow in SolidWorks for both the theoretical and demonstration models, then implementing or fabricating any required parts for the demonstration model, assembling those parts, and then testing them. If there needs redesigning, we have a 5-day gap for that, and if further testing needs to be conducted, we have another 5-day gap for that. Then we have 14 days to write the final report and presentation in order to be finished by April 19th.
Right here is our reference list. We would like to thank you for your time, and we would like to let you know that we are very eager to show off what we have learned here in the Mechanical Engineering Technology program at Alfred State College.